Hello. In this video tutorial, we're going to be taking a look at Skills Practice 23.2, Refraction. Please remember to pause or rewind the video as necessary. Let's begin. Read along with me, please. When light rays cross from one material to another, they bend. This bending is called refraction. So refraction is the bending of light when when that light passes from one material to another material. And we call that material a medium. All kinds of optics, from glasses to camera lenses to binoculars, depend on refraction. If you're standing on the shore looking in a stream, the fish appears to be a slightly different place than it really is. That's where it appears. That's where it is. That's because the light rays bounce off the fish are actually refracted at the boundary between the water and the air. If you're a hunter trying to spear the fish, you better know about this phenomenon or the fish will get away. Okay, so why does this happen? Because the light rays are refracting at the surface. Hence, the fish is actually closer than it appears. Why do the light rays bend as they cross from water into air? Well, light rays bend because they travel at different speeds in different materials. In a vacuum, like outer space, light travels at the speed of 3 times 10 to the 8 meters per second. But when light travels through a material, it is absorbed and re-emitted by each atom it hits. Well, that absorption and re-emission slows down the light. So, we experience this slowdown as a bend in the light ray. The greater the difference in the light ray's speed through two different mediums, the greater the light bends in the pathway of the ray. The index of refraction, which is the variable n, for the material is the ratio of the speed of light in a vacuum to the speed of light in that material. Okay, so this variable is n, this variable is c for a vacuum, and this variable is v. So n equals c over v. The table below has some common materials, common index of refraction for common materials. So the vacuum of outer space would have a index of refraction equal to 1. Air is very close to that, more or less basically equal to 1. Water, well, the molecules are closer together in water. So that means there's going to be more absorption, re-emission of the light, which means it's going to go a little slower, right? It's going to bend a little more in water. Higher index of refraction. Glass, a little higher index of refraction. And finally, a diamond, right? Even higher. So could the index of refraction for material ever be less than 1? Explain. So for question number 1, why can the index of refraction never be less than 1? Well, 1 is the lowest value you're going to get. Well, let's do a numerical example and see why. Well, the speed of speed of light in a vacuum is, we saw it right here, 3 times 10 to the 8 meters per second. So let's use this equation here to calculate. So n equals c over v. So the speed of light in a vacuum is 3 times 10 to the 8 meters per second. Well, it turns out that the speed passing through, let's say, a vacuum, the actual speed of it is going to be the same as the speed of light in a vacuum. And you can see that's going to equal 1. Now, since v, the speed of light in a material, can never be greater than c, the speed of light in a vacuum, n will never be less than 1. Right, 1.0. So Let me write it like that instead. Explain why the index of refraction for air is smaller than the index of refraction for solid glass. Well, this is because light, I just used this formula here, N equals C over V. And if we compared the N for air and the N for glass, the speed of light in air is much greater. Therefore, the index of refraction is much lower. Glass, however, the speed of light in glass is much lower, so the index of refraction, therefore, is much bigger. So light travels faster in air than through glass. Let's take a look at an example. Calculate the speed of light in water, glass, and a diamond using the index of refraction and the speed of light in a vacuum. Okay, so we're looking for the speed in all of these substances. So we're looking for V. We're looking for V. And what I'm going to do is I'm going to break this down into, kind of like a part A, B, C. And I'm looking for V in water. I'm looking for V in glass, the speed in glass, speed of light in glass. And I'm looking for the speed of light in a diamond. Okay, we're given C. C is the speed of light in a vacuum. And for part A, B, and C, we're also given the indices of refraction, N, which you can get from these tables right here. So air is 1, glass is 1.5, and a diamond is 2.42. So we're doing water, I'm sorry, water. So N for water is 1.33. N for glass is 1.5. And N for a diamond is 2.42. Now the equation we're using is N equals C over V. And to solve this equation for V, we're just going to do a little switcheroo right there. And therefore, V is equal to C over N. Let's divide this into 3 segments and perform the calculation 3 times. So V equals C over N, which would be 3 times 10 to the 8 meters per second over 1.33. Okay, put that in your calculator right now. 3E8 divided by 1.33. And we're getting a speed of about 2.26 times 10 to the 8 meters per second. So very fast. Okay, and the second one, same idea. We're going to go C over N, so 3 times 10 to the 8. Divide that by 1.5. Okay, go ahead and put that in your calculator. 3 times 10 to the 8 divided by 1.5. And we get about 2 times 10 to the 8 meters per second. So that hopefully should make sense, because if you look at the numbers here, this denominator is greater than this denominator, therefore this speed should be less than that speed. And finally, V equals 3 times 10 to the 8 meters per second over 2.42. So 3 times 10 to the 8 meters per second divided by 2.42, and we should get about 1.24 times 10 to the 8 meters per second. Please make sure you practice these calculations yourself independently. Okay, When a light ray moves from water into air, does it slow down or speeds up? When light moves into air, it speeds up. If we're going from water into glass, glass is a higher index of refraction, more optically dense. Therefore, when light moves into glass, it slows down. In this next section, we're going to take a look at which way does the light ray bend. Now let's look at some ray diagrams showing refraction. To make a refraction ray diagram, draw a solid line where the boundaries between the two materials. So in other words, that line right there, between those two materials. Then you're going to use arrows to represent the incident and refractive rays, and the normal is drawn with a dashed line that's perpendicular to the boundary between those two surfaces. You can see the light ray is bent toward the normal as it crosses into water, a higher index of refraction. Light rays always bend toward the normal when moving from a low index of refraction to a high index of refraction. So let me summarize that. Light bends toward the normal when moving from a low index refraction to a high index refraction. Okay, now, light rays bend away from the normal when moving from a high index refraction to a low index refraction. Okay, so what we're going to do in each of these next examples, oh, by the way, the amount of bending depends on the difference between the two index fractions. If there's a great difference, there's going to be a lot of bending. If there's very little difference, there's going to be slight bending. So we're going to draw a ray diagram for each one. I'm going to reproduce this for each one. There we go. All right, so the first one, we're going from water into plastic. We have a light ray here, and look at the indices of refraction. 1.33, 1.59. So if this is N1, this is N2, we're going to bend closer to the normal. Here's theta 1. Theta 1 is our angle of incidence. Theta 2 here is our angle of refraction. And you can see we've bent closer to the normal. Okay, now we have a light ray moving from 1.77 into air, which is 1. Okay, so sapphire. Into air. So you have, this time you're going from 1.77 into 1. That's a pretty large difference. So it's going to bend not only away from the normal, but very away from the normal, because that is a large angle. So here's our theta 1, our incident angle, and our theta 2, our refractive angle, is really large, far away from the normal. So we are bent farther from the normal. Okay, and in this example number 8, we are moving from, so it's asking which light ray will be bent more, one moving from a diamond into water, okay, or one from a sapphire into air. Now, we don't necessarily need a ray diagram for this one per se, but we need to think about the differences. So if we look at the differences there, so from diamond into water, the difference in those indices of refraction, 2.42 minus 1.33, is 1.09. From sapphire into air, the difference between your indices of refraction there is essentially 0.77. So there's a greater difference. Greater difference bends more. From diamond into water, we bend more. In this next section, we're going to now quantify the refraction angles that are being bent. And we're going to do that using the Snell's law of refraction. We're going to use the equation called the Snell's law of refraction. N1 times the sine of theta 1 equals N2 times the sine of theta 2. The nice part about this is that there are only 4 variables to worry about. N1 is the index of refraction of medium 1. Theta 1 is the angle of incidence. N2 is the index of refraction of medium 2. And theta 2 is the angle of refraction. Let's put this into action. Number 9, read along with me, please. Air has an index of refraction equal to 1, and glass has an index of refraction equal to 5. Light travels from air into glass. So there's the first medium, there's the second medium. Always try and figure out where light starts and where light finishes. Since the light starts in air, air has an index of refraction of 1. We're going to call that N1, the first medium, index of refraction of the first medium, which would make the glass index of refraction of 1.5, we would make that N2, because light ends in glass. We have an incident angle, theta 1 of 25, and we're looking for the refractive angle. So theta 2 is our unknown. In our given box, we're going to list N1, N2, and theta 1. So N1 is 1.0, N2 is 1.5, theta 1 is 25 degrees. Okay, and in addition to this, we're going to draw what's called a refraction diagram. Let's start with air, glass. Since I am moving from air into glass, which is a higher index of refraction, more optically dense medium, I'm going to be bending closer to the normal. So how do we label this? Here's theta 1. Here's theta 2. We're going to use our Snell's law equation. N1 times the sine of theta 1 equals N2 times the sine of theta 2. Now, go ahead and copy down this equation one more time over here. And we are solving for theta 2. So in order to solve for theta 2, you have to isolate sine of theta 2. Now, in order to do that, we're going to go ahead and divide by N2. Like that. The sine of theta 2 is equal to N1 times the sine of theta 1 divided by N2. Notice I just reversed the order of the equation. I just flipped everything around. Now, we're going to plug in N1 is 1. So we're going to go 1 times the sine of theta 1. Theta 1 is 25 degrees. Over N2, which is 1.5. Okay, now what you're going to do is you're going to put all of that in your calculator. Okay, let's see how this looks in our calculator. I'm going to start off by taking the numerator part here, sine of 25, and then times 1.0, right, is 0.422. Then I'm going to divide that by the 1.5. And we get about 0.2 174. Basically, we don't need all those digits, okay? Because here's what we're going to do. We need to solve for theta 2. And if you remember in class, we did that by taking the arc sine of both sides of the equation. In other words, the arc sine of sine and the arc sine of the decimal. Well, the arc sine of sine cancels, right? Leaving you with the angle that we're looking for, theta 2. And taking the arc sine of the decimal is very easy to do, because now all we need to do is go hit our second function or shift button and then hit your sine button again. And we get roughly about 16 degrees. Okay, now this answer makes sense because our initial angle was 25. Our refracting angle is 16, which is less than 25. See how we refracted closer to the normal? Let's look at another example. Number 10. Light travels from glass into air. So that's the first medium, that's the second medium. The incident angle is 30 degrees. What is the angle of refraction? So N1 is now glass, which is 1.5. N2 is air, which is 1. Theta 1 is still, well, no, it's not still. It was 25 earlier. Now it's 30 degrees. And if we draw a refraction diagram for this, let's put glass up here and air down there. And we start with an angle theta 1. We're going to be bending farther from the normal. We expect theta 2 to be bigger because we're going into a less optically dense medium with a lower index of refractions. In that case, it bends farther from the normal. We are going to use our Snell's law equation. Write it down one more time. Recall we are solving for theta 2, which means we need to isolate again the sine of theta 2. We do that by dividing away n2. We're going to reverse the equation and start plugging into it. So sine of theta 2 is equal to n1, which in this case is 1.5, times the sine of 30. And we're going to divide that by n2, which is 1.0. Okay, put that in your calculator right there. And sine of 30 is a half, times 1.5 is 0.75, divided by 1 is 0.75. Now, to get your missing angle theta 2, just take the arc sine of 0.75. And you get about 48.5. We'll just round it up to 49 degrees. Okay, again, this answer should make sense, because we started with a 30-degree angle and we bent farther from the normal. And 49 degrees is greater than 30 degrees. Number 11. Light travels from air into diamond. Air being the first medium, diamond is the second. The index of refraction for the diamond is 2.4. Since diamond is the second medium, that would make this N2. The incident angle is 30 degrees. What is the angle of refraction? So we're still looking for theta 2, the angle of refraction. We are given N1. That would be air, 1.0. N.2, we are given 2.4. Theta 1, we are given 30 degrees. Let's draw a quick refraction diagram of this. Let's see, I'll put air up here and a diamond down here. Light is going through air. And let's talk about a beam of light that's going at an angle like this. It's going to be bending into a more optically dense medium, which means it's going to bend way closer to the normal. There's our theta 2 right there. Very, very small angle. Use your Snell's law formula. Write it down one more time. Again, to solve for theta 2, you need to isolate sine of theta 2. We will do that one more time by dividing away n2. And the sine of theta 2, when we plug in, n1 is 1 times the sine of 30 over n2, which is 2.4. So we have sine of 30 is a half over 2.4, and we get roughly about 0.2083, and there's repeating decimals after that. Take the arc sine of 0.2083, and we will get about 12 degrees. It's 12.024699. You don't need all those digits, just round to the nearest degree. Okay, that answer should also make sense because we started with a 30-degree angle. We said that in a diamond, you're going to bend very close to the normal, meaning small angle of refraction. And indeed, we have a 12-degree angle for that. Number 12, air has an index of refraction equal to 1, and glass has an index of refraction equal to 1.5. In this example, light travels from glass into air. In other words, glass is the first medium. That would make 1.5 N1, and air is the second medium, which would make 1.0 N1. Or excuse me, N2. N2, second medium. Calculate the incident angle. We are now looking for theta 1. When a refractive angle equals 90, that's theta 2. Okay, that means you're given N1, you're given N2, and you're given theta 2 is 90 degrees in this example. N1 would be glass, that would be 1.5. N2 would be air, that would be 1.0. And this time we're going to draw a slightly different ray diagram, refraction diagram. This time I'm going to start with glass down here and air above it. I'm going to start with light actually here in the glass going upward instead of downward. I can do that. That's fine as long as I have arrows indicating the direction and as long as I have my angles labeled appropriately. Theta 1 is now down below. Now, to refract 90 degrees from the normal means you are refracting along the surface like that. There is your theta 2, which is 90 degrees. Use your Snell's law of refraction formula. N1 sine theta 1 equals N2 sine theta 2. Write it down one more time. This time, ladies and gentlemen, we are solving for theta 1. And in order to accomplish that, you need to isolate sine of theta 1. Well, to accomplish that, you need to divide away N1. Okay, so sine theta 1 is equal to N2, which is 1, times the sine of theta 2, which is sine of 90, all divided by N1, which is 1.5. So sine of 90 is 1, times 1 is 1, and so we have the sine of theta 1 is going to be basically 1 divided by 1.5. Which is basically a repeating decimal. And if we take the arc sine of 0.6667, we will get an angle theta 1, not theta 2, sorry, of about 41.8. We'll round that up to 42 degrees. And finally, number 13, we have an example where light travels from water into air. So water is the first medium, air is the second, with a refracting angle theta 2 of 90 degrees. Calculate the critical angle, or theta 1, Theta 1 is the unknown. For the water-air interface, the index of refraction for water is 1.33, that would be N1, and 1.0, that would be N2. So N1 is 1.33, N2 is 1.0, theta 2 is again 90 degrees, and if we were to draw a picture of this, I could start with water down below, air above. I could start with a beam of light that is going up to the water-air interface. Your theta 1 is down here. And I'm refracting 90 degrees, theta 2 90 degrees from the normal, which means I'm refracting along the surface. N1 sine theta 1 equals N2 sine theta 2 is our formula. Write it down one more time. To solve for theta 1, we need to isolate sine of theta 1. We will accomplish that by dividing away N1. And so sine of theta 1 is equal to N2, which is 1.0, times the sine of theta 2, which is the sine of 90. Divide that by N2, which is 1.33. So all of that's equal to 1. And 1 divided by 1.33 is about 0.7518, roughly. Anyway, take the arc sine of that decimal, and you will get an angle, a critical angle, a theta 1 angle of about 48.7 or 49 degrees. I hope you found this video tutorial helpful. Please remember to pause or rewind as needed. See you next time.